The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Okay, our next speaker is Peter Emmons to talk about, I don't have the wrap down numbers written down here, but I think it's 4, 5, and 7, not necessarily in that order, and it has to do with surface repair by a number of different form and pour techniques.
Okay, thanks, Dave. So we're going to cover basic concrete repair in these 3 different wrap documents. Horizontal repair, that would be on a floor. Vertical and overhead repair on walls and ceilings using a technique called form and pump, and the other technique is related to that. It's called form and pour. So I'm going to cover surface preparation, which will be applicable to all 3 of these different techniques. And then I'll specifically talk about these 3 techniques from a placement standpoint. They're all unique, the full depth, the form and pour, and the form and pump. And then the quality assurance and quality control, I'll be talking about that. That's appropriate for all these techniques. And the answers to these questions is one of the goals of this talk, is understanding the purpose. Why are we doing this? When do I use these different techniques? How do I prepare the surfaces? What are the safety considerations? Pre-construction and trial repairs. When do I do that? Repair procedures, which is really the core of this discussion, and how to check for the quality. So we talk about surface preparation. We're dealing with concrete deterioration, and a lot of deterioration is really related to corrosion of embedded steel. In some cases, it's freeze-thaw damage. But specifically, I'll be spending most of my time talking about corrosion-related damage. We go through a process. We have the existing structure, the existing problem, the deteriorated delaminating, spalling concrete, rusting, reinforcing steel. We have to go through a cleaning stage, a purging of the structure of all this bad stuff, and get it back down to a solid, sound substrate. And that's going to be followed by some kind of placement technique, which are the 3 techniques we'll be talking about. Up to about 1989, the procedure for preparation wasn't too involved. It was knocking the loose stuff off and then putting stuff back. We've learned a lot in this industry over the last 30-so years, and we've developed a practice that does a lot more than this old method of just knocking the loose stuff off, and I'm going to show you that technique. It's very important to the quality of repair. It's very important to the longevity of the repair. So one of the things that we learned is that you need to use power equipment. You can't just use a hammer and knock the loose stuff off. You need to use power equipment. The most common tool for concrete repair like this is a 15-pound pneumatic chipping hammer. They also make hammers that are pneumatic and electric, but for contractors that are in this business doing this all the time, the pneumatic chipping hammers are the most effective, most powerful, and the most cost-effective. The standard of practice today is to remove concrete around the reinforcing steel wherever corrosion is present. It doesn't matter how much corrosion is present. If corrosion is found to be present, the minimum standard, and there's one exception I'll show you in a moment, is to chip around the bar about 3/4 of an inch so you can put your hand around it. This is in accordance with the International Concrete Repair Institute Guideline 310.1R. This guideline was developed in 1989 and is held fast as a standard for this preparation. It's probably the single most important thing you can do to get a quality repair, is you got to remove the environment that has caused this problem. So in the old days, we just knocked off the loose stuff, and the bad, the stuff underneath the bar would remain, but they were still contaminated with chlorides or carbonation. So by removing the concrete around the bar, you're going to replace it with a uniform chemical environment with the new material. And that's very important for the corrosion process not to reignite itself. When you start to remove concrete, you end up with some odd shapes. One of the things that we've learned is to take these shapes and make them more uniform. You know, there's some kind of thing that has caused this concrete to deteriorate in that exact location, and you have to ask the question, why did I stop there and do all this? This is not good practice. The recommended practice is to create these odd shapes into uniform shapes, because the environment that caused this problem has not manifested itself in the immediate adjacent area, but certainly will. So the diagram on the right is the recommended practice. When we're doing beam bottoms and slab edges, we want to create square cuts. We want to true them up, as you can see in these diagrams, whether it's a shallow partial depth repair on a slab edge, or the beam bottom. There's one exception to this, and I'm going to talk about this. It's very important from a structural standpoint, and that's when we're working on columns. You can see this column is delaminated. It has rusting reinforcing steel. And when we start looking at this from a load-carrying member, our column carries compressive loads, is when we start removing the concrete around that reinforcing steel. As you can see in the picture on the left, you can take a lot of section out of that column. Obviously, you can put shoring in there to feel good. But what we've learned is that when you remove that concrete and you come back and replace it, you've taken out concrete that was under stress. This is inside the reinforcing steel cage. So if the concrete is under stress, it was compressed, and you're chipping it out, you're transferring the load to the remaining concrete. Now, when you go back and put the new concrete in, it has no stress. As a matter of fact, it may be in a tensile state because of the shrinkage of the repair material. So you can't reestablish that compressive load that was in there with the new material. So you're basically creating potentially an overstressed situation in the remaining concrete. So what we have in our guidelines, ISRI guidelines, the same one I mentioned about surface prep, when you're working on columns, you need express permission by the engineer of record to chip inside the cage. And what we're finding is the engineering community goes in and they do analysis and see what the load levels are if you do remove the concrete around the reinforcing steel. That is good practice to remove around the reinforcing steel. But it's not good practice if you're compromising the structural integrity. So the procedure, as you can see in these diagrams, we start by sounding the concrete where it's hollow. We put a paint mark, and we outline it through that process. And then we take our chipping hammer and we start removing the concrete down to the reinforcing steel, removing the laminated concrete, and we start to see what it's looking like. And we chip and remove the concrete until we reach steel that's not corroded. As you can see in the third diagram right here, we've removed the concrete, and we're starting to see, especially in this fourth location, the boundaries of the corroding reinforcing steel that caused the delamination that we marked out. And you can see schematically that there's some clean bar around the perimeter. Then the next step is to take a hammer and sound it again. You can see the hammer is sounding the concrete, listening for hollow sounds, delaminations, make sure that the boundaries are about right. And once they're established about right, then the edges are squared up with a saw cut around the perimeter. And then that's followed by some more chipping to remove the concrete between what was already chipped and the saw cut, leaving the final stage here, which is the concrete removal is complete. The concrete is cleared underneath. There's clearance underneath the bars. It's square-edged. And that leads us to a discussion about the saw cut. Saw cuts allow us to create a vertical edge around the repairs. It's very important, obviously, not to compromise any reinforcing steel. You need to know where the reinforcing steel is located so you don't cut through the bars, and allow a shoulder to be created through the saw cutting action. From a safety standpoint, people that are chipping concrete day in and day out, like a lot of the companies that go out and do this kind of work, there's a lot of wear and tear on the body, and there's a lot of issues associated with the ergonomics of using these kind of demolition tools. So it's very important to establish the proper posture and procedures for the people to use these tools. You know, the basic setup of a chipping hammer is run by an air compressor. It goes through a receiver tank, which is just a storage device. It's also a storage device that collects water. And there's an oiler connected to the line, which oils and lubricates the chipping hammer. That's the basic mechanisms for doing this kind of work. When we talk about exposing these reinforcing steel bars, we have some things that we like to do because we're trying to reestablish a clean substrate and place material. So a lot of the bars that have been corroding are necessary that we clean them so we don't have bond-inhibiting materials. So we have a lot of flaky, rusty materials that have to come off. We want to clean them down so we don't have bond-inhibiting materials. So we want to, at the minimum, clean these bars such that they're in the same state that you would have in new construction. There may be some light, tight oxide on them. That's acceptable. But heavy mill scale needs to be removed. In some cases, these bars may be coated, specified by the specifier, and you need to follow the recommendations in the specification or the manufacturer's requirements for the degree of sandblasting. So what we're trying to do is clean those bars. We have rusty bars. And the most typical method of cleaning bars in a production job is using abrasive blast. In some cases, that's not permissible by some of the environmental rules and jurisdictions, but in most cases, that's the way it's done. It does a great job, and it cleans the bar, removing of all the heavy oxides and that sort of thing. And depending on the degree required, it may require more time to get the different levels of cleanliness. On some jobs, a wire wheel on a grinder will suffice, especially in a small repair. In some cases, the bars, once they have started to corrode, they're losing their cross-section. The native steel is converting into an oxide. It's reducing the cross-section. When you run into these kind of situations, it requires the licensed engineer to really direct us on how to take care of this particular dilemma. In some cases, there's not enough lost cross-section. In some cases, the lost cross-section compromises the structural integrity, and some type of rework of the steel is required. So now we move from the preparation, which is kind of standard for all these procedures we're talking about, and we talk about how we're going to place the material. And we're going to talk about the moisture condition of the substrate, how we create the bond, we use bonding agents or not, and our placement techniques along with quality assurance. So the basic concept is pretty simple. And if you follow these, you'll have excellent repairs that will last a long time and stay bonded. So we have a surface that's been chipped away of all its bad, deteriorated concrete. There's no delaminations left. It's solid substrate. You can take a hammer and you ping it, and you hear the pinging sound. But there's still a lot of dust on the surface and other things that are clogging the pores. So think of concrete like a hard sponge, and you want to open up the pore structure of that hard sponge. And we do that with sandblasting, abrasive blasting. We do that with high-pressure water, and it opens up that hard sponge, the pores. So that when you think about that hard sponge, and if you take a sponge and you put it, take it on the counter where you spill some water, it starts soaking up that water. Well, the concept of bonding is exactly the same thing. It's a mechanical connection between the new and the old through absorption. So we open up these pores, and you have a liquid material. It could be the repair material directly, or it could be a bonding agent that's separate. It's sucked into those pores, and that's what creates the connection between the two. It's all mechanical. There is no chemical. When we talk about chemical and mechanical bond, this is all interlocking mechanical bond. And it all comes through that pore structure. So keeping that pore structure open and clean is absolutely critical to a successful bonded repair. Peter Golter in the earlier presentation talked about 425 psi. That's what we're looking for is that kind of connection, a tight connection. Next thing I'd like to talk about is water and getting the surface conditioned. There's a lot of different theories on this, but I think it comes down to a simple thing. If we understand that the concrete is a hard sponge and we want to connect the new and the old together, we've got to keep the pore structure open. If we put water on the surface and clog the pores, as you can see in this middle graphic, there's no pore structure for the material to be absorbed into. This is the absolute worst condition that you can create. So if you're out there hosing down the repair and filling up those pore structures with water, and you're immediately coming back and putting a repair material down, you're not going to get a good bond at all. It will actually be a bond inhibitor. So our ideal state is either dry condition or saturated surface dry. And to determine exactly which is the right procedure, my personal philosophy is that, if you can do something dry, then you've eliminated a risk of being too wet. So the general concept, though, is that we would like saturated surface dry. We don't want the substrate to suck so much water out of the new repair material that it causes a detriment of the repair material. So how do you determine these procedures? We'll talk about that, how to optimize this for the specific jobs that you might have. So let's talk about bonding agents. Now, bonding agents, we've learned, and there's a lot of technology out today, that they may not be necessary. 20 years ago, the theory was you have to have a bonding agent, and many federal transportation agencies, Corps of Engineers, and other authorities have done a lot of testing and determined that in many cases they're not necessary if you have that open pore structure and you create the intimate contact with your placement techniques. The most common type of bonding agent is, and the most basic, is a sand cement slurry, and you can see in this substrate, it's just broomed in. It's one part sand, 1 part cement made into a slurry, and it's broomed into the surface. And of course, it's not allowed to dry out, otherwise it'll be a bond breaker. So that's the risk with any of these bonding agents, that if they're not done properly, they can become the opposite of what they're intended to do. One of the ways that you can assure that your procedure, depending, every job is unique in repair, every substrate is unique, and a way to identify exactly what kind of surface preparation technique and moisture conditioning is required is to actually do some trial mock-ups and do some testing. As you can see here, we're testing out 3 different procedures. One way to evaluate these different procedures is to take a core through the new material into the old and then do a uniaxial bond test, which is gluing a steel dolly or aluminum dolly to the surface of that core while it's intact into the substrate, and then applying a tensioning device onto that dolly and measuring the pressure that's recorded on the gauge and dividing that by the area of the core, and that results in a result. And I'll reference a couple test methods in a moment that talk about how to evaluate those results. You can also look at the visual results. You can see the new and the old. You want that intimate contact to create that connection. You can't get absorption unless you have the intimate contact. These are the 2 test methods that are available. There's an ASTM test method, 1583, and ICRI has an excellent guideline that talks about this test method and how to use this test to and measure the results and evaluate the results. So once we've gotten through our procedure on how to get this surface condition, we're going to talk now about placing the material. Now, when we place material into these prepared areas, we need to accomplish a few things. One is we want to encapsulate the embedded reinforcing steel. So there's no shadows, there's no honeycomb, and it's all uniform throughout the cavity. The other thing is we have to create intimate contact. Whatever method we're using to place this new material, it has to get into intimate contact. That means there's some kind of pressure, there's some kind of liquefaction, and I'll show you some of that with our different procedures. And that's where we create the absorption, the suction into the pore structure. And that's the connection we have to have. A lot of mistakes are made by not allowing this to happen. So the first placement technique I'm going to talk about is our repair application guide number 7, which is full and partial depth slab repair. That's horizontal repairs. And the first one I'm going to talk about is full depth. Now, full depth is very similar to new construction. We are basically building formwork from underneath and establishing good reinforcing steel. A lot of times, because of the volume and thickness of these type of repairs, the common material will be ready-mix concrete with a low water-cement ratio, about 0.4. And we're going to place the material into that prepared area. We're bugging the concrete in this particular case. It could be pumped, and then it's vibrated, and it's followed by the normal construction process that you would see on any new construction job by screeding, floating, and any other additional finishing that's required. And then that's followed by a curing with curing compound, wet burlap, same exact procedure you'd find for new construction. If it's partial depth, which means that we've only taken out the top surface of the slab, what we're going to need to do is basically place the material in there, and you can see the vibrator. The vibrator creates a liquefaction of the concrete that's in there, and that when the vibrator is turned on, the slump goes to a very high slump, and it liquefies, and that liquefaction allows the absorption into the substrate. And the typical materials that are used for these partial depth repairs are ready-mix concrete and packaged repair materials, the kind of materials that are made by manufactured companies that specialize in repair products. And for the most part, these are cementitious, Portland cement-based materials. So in summary, preparation is a critical step in achieving long-lasting repairs. I can't overemphasize that. You know, chipping around the bars, removing and getting a uniform chemical environment will ensure a long-lasting repair. Along with that, we have to open up the pore structure. It's a very simple process. Sometimes it's tedious, but has to be done in order to achieve good bond. No bonding agent, no special material is going to overcome a poor, dirty substrate where the pores are clogged. You have to open up the pores. The placement technique has to create intimate contact. All these different techniques I showed you with vibration, with form pressure, have created intimate contact. It's filling up the cavity. It's allowing that material to be absorbed into the old substrate. You have to measure quality. You know, the pull testing technique is probably the most important technique that measures the quality of the interface between the new and old. We want to create the bond, and needs to be done. All the traditional quality methods of measuring compressive strength can be done, certainly slump and air content depending on the application. So that concludes my presentation on those three techniques. It's really Concrete Repair 101. And if there's any questions, we'll entertain those. Carl?
Do you ever consider using shrinkage compensating cement?
So the question is shrinkage compensating cement, so like a type K cement. So what we found, and early on in my career, I thought that would be the answer to reducing shrinkage cracks using expansive shrinkage compensating cement. And what we found is that those cements expand in their plastic stage, and as long as they're allowed to expand, they come back to the same place. But in a repair, we're confining that material, and it can't expand, so we get the same amount of dry shrinkage as we would with traditional materials. So we have no benefit that we've seen from that. That's a good question.
What about air trapping at the top?
Air trapping, you know, everybody says there's air trapped up there. So it's very important, depending on the procedure, is that when you're chipping the concrete, if you have any spots that could be an air trap, we drill a hole through the form and put a PVC tube up there with a little bevel on it, like a 45, and it bleeds the air out. So when we're pumping it, actually grout will come right down that tube and bleed out any air. That's a good question. Doc?
Video you couldn't show, like going to YouTube and just putting in self-consolidating. There are a series of job site videos come up, so anybody wants to see it, it's on YouTube.
Yeah, self-consolidating to me has been the best breakthrough for our repair industry from a material standpoint of anything, because it just reduces the steps, improves the quality, and reduces the cost to the client. Yes?
Any of the projects we're working on, Peter, at the parking garage have already been repaired previously. And so now we're encountering a situation where we have parent concrete adjacent to repaired concrete, and we have spalls encroaching upon repairs and the parent material. What has been your experience with making repairs adjacent to previous repairs and material selections for them?
That's a great situation. People start out repairing a repair at a time, and then time progresses, and the same conditions are existing, and the next area starts to spall and to laminate because the chloride thresholds and the corrosion thresholds are taking place. So you end up with a mishmash of repairs. And what happens, we see, is the long-term owners, they realize that you can start repairing, but at some point it makes sense to repair the whole surface. So you would go in and hydrodemolition, as an example, on a deck, on a parking deck. You may do mass removal of the top layer around the top mat, and then come in with an overlay and integral repair at the same time. So a repair against a repair is just fighting time. It will certainly allow it to be postponed, but probably be more costly than just doing a global repair. But that's a great situation that we see so many times. Yes, back there.
Do you get into any guidelines for people on spacing of the sheets depending on thickness of the air and type?
Okay, so in the form and pour where we're pouring it in, if you're using a self-consolidating concrete, it can go 25 feet in all directions. If you're using a more traditional mix that needs a lot of vibration, you're going to have to put a chute every 3 or 4 feet in some cases. That's what, the kind of range. It's not 25 feet, it's not 10 feet. It's in that, depending on the depth and width and that sort of thing. In the back there?
Are you using plexiglass just for demonstration purposes, or are you using common quality control technique?
Yes, great question. The plexiglass, we love plexiglass because we put it on a lot of our jobs so that we can see what's going on and where it is. And because we have as we pressurize that form, when that form, you can imagine that guy's pumping concrete and that volume is being filled up. Now, what happens if you keep pumping? You'll blow the form off. So you have to have very close radio communication with the operator to make sure you're putting enough in there that makes the formwork, you can feel the load, you can hear it creaking. You know you've got load in it. And some jobs, we actually put load cells in the forms. For critical applications, we can actually measure the pressures to know that they're filled. But the plexiglass demonstrates to everybody, so it's an easy thing to do. So it is a quality assurance program that you have. And it really demonstrates to all the stakeholders, the procedure, and it helps train the people that are doing the work.